In this talk, I will explain double coinvariant rings of pseudo-reflection groups, which are analogs of the equivariant cohomology rings of Frank manifolds. In the case of pseudo-reflection groups, not while groups. So, let me make a brief review of GKM theory. In this session, we consider a Frank manifold. A Frank manifold G over T, where G is a compact connected real Lie group and T is its maximal torus. T acts on G over T by the left multiplication. And the cohomology ring is the equivalent cohomology ring is defined by the ordinary cohomology ring of the Toric construction. The inclusion map from the fixed point set to the Frank manifold induces this map. This map is called localization map. Because the fixed point set is identified with the while group, this is isomorphic to this ring. We identify this to this with the map we identify this ring with this ring of all maps from W to H star VT. It is well known that this map is injective. So, when we want to know this ring, by mapping the elements of this ring through I star, and we can see it. You can see the element as the map from W to H star VT. The GKM theorem, proved by Gorski, Kotovitz, McPherson, is as follows. And Fw minus f of sigma alpha W is contained the ideal alpha generated by alpha, where sigma alpha is reflection corresponding to alpha, and for every root and for every W, yes, in the while group, and this description relates to the Boolean decomposition let me write S for the CW complex, which is GOT as topological space. Where CW is T invariant cell, and dimension of CW is twice of the length of W. Yes?
I wonder whether people know the cohomology groups of this G mod T or not.
Sorry.
Do people know the cohomology groups of G mod T? So it's very. Oh, okay. So the Beatty numbers are people know. Oh no. Okay.
Yes. Yes. Especially, we know this cell decomposition. So the batch we can calculate the batch numbers of the flag manifold by calculating the distribution of the length of elements of Y groups of the Y group, right? Only this decomposition has only even dimensional cells. Okay. Cell structure.
The number of these cells are just the vector numbers.
Okay.
So the number of cells in this decomposition is the number.
Just the vector number.
No, I'm determined by Y group.
Yes. Yes.
Yeah.
Okay.
So the Zell skeleton is on the point which corresponds to the unit element. The length of the simple reflection is 1, so the one skeleton is this, and this is a radial 2 spheres. So I draw some picture. This S2 is a connected component of a fixed point set fixed by some codimension 1 subtorus T prime, where T prime is defined by where hat is the coroot corresponds to alpha. So this is to T rotates this S2 by alpha. And we can easily the equivariant homology ring of this S2 by the Meyer-Beatrice sequence. Actually, precisely, sorry. Precisely speaking, I have to write here for the north, the upper hemisphere, but it is contractible, so. This and this one. Yes. Here is and this is nothing but and so this is isomorphic to this ring. Here is the localization map. And every ring has vanishing odd paths, so we assume that it's zero. Yes. The GKM condition, this condition is called the GKM condition. The GKM condition is nothing but the calculation of the Meyer-Beatrice sequence. Right? You see? So, yes, the image of the localization map, and we calculate the difference of these two elements. Then it is in this ideal. And if we attach the high dimensional cell, we have to consider. Oops. The root space composition, yes, the root space composition alpha and sigma alpha W is smaller than W in the viewpoint of the Breuer order. This is the complex numbers. These are complex numbers, and with a map from T as a capital alpha. what I want to say is that the GKM condition is comes from the Meyer-Bidder sequence, and comes from the Boole decomposition and its Meyer-Bidder sequence. Complex reflection, so oops. Now I define unitary complex reflection group. So to define it, let be C vector space and automorphism. Linear map sigma is a pseudo reflection if and only if dimension sigma, so sigma fixes some hyperplane. Yes, C. And this, we assume that the order of sigma is finite. Finite group W is a pseudo-reflection group. If and only if W is in GLV and it is generated by pseudo-reflections. So, yes, of course. Yes, of course. The simplest example is we regard this as the nth root of unity. And we consider invariant elements, coinvariant rings. So first we consider what is the invariant elements of CV. The polynomial function, the ring of polynomial functions on V. So this is polynomials in X, where X is another element of V star, and I define the double action on V star by this question. Here defined by CW of so a coinvariant ring is and this is isomorphic to I always confuse when I define the double action V star. So let me verify this definition. This definition natural. So let V is three-dimensional vector space, and W is what's it? Well, three. I think it means T4 is T1. Oops. T4 is T1. And xi is element of V star defined by connector delta. So let me calculate this element by definition. J equal 2. So x1 dot w is x2. I think my action of w on V star is natural. I think. The double coinvariant link of W is this quotient ring. This is analog of the equivalent cohomology ring of flag manifold with C coefficient. And we also have the map from here to here, map WCV defined by A times B acted by W. So the function which maps W to this element, and ordinarily also coinvariant wing is 0 times tensor star. So the left CV comes from the Borel construction. Zero じゃないか。ゼロってか、ゼロって C、sorry, C. Yes, C. Not zero. I'd like to say this is zero. Not zero. Yeah. And to
W is acting on the right.
no, say both side.
W is acting on the right.
Yes. And to describe the double coinvariant rings in the similar form of GKM condition, of GKM description, we have to choose for each reflection sigma, we have to choose E star where yes, and we write a sigma for this hyperplane. Yes. And it is known that the stabilizer of H sigma is a cyclic group, a finite cyclic group. Oh, sorry, I forgot some explanation. If sigma is pseudo-reflection, then by choosing nice basis of V, we can write sigma as matrix representation yes corresponding to nice basis, some basis, we can write sigma as this form. So lambda is yes, root of unity.
Excuse me, I'm a little confused. So if you have a reflection, how do you choose alpha sigma in the field space?
So sigma fixes some
Pseudo-reflection or?
sigma is pseudo-reflection. Sorry, pseudo-reflection. Sigma fixes some hyperplane, complex codimension 1 subspace, and we choose some element V star, yes, a linear form which vanishes on the hyperplane.
Okay. I'm sorry. You wrote below. I mean, you wrote down the next condition. This is how you choose alpha sigma.
Sorry. I explained this fact. Okay. Now. The one by McDaniel. The image of I star is can be described by some condition, but complicated condition. Oops. Whereas this denotes the order of sigma, and W for every element of the pseudo-reflection group. Contained in this is non-trivial eigenvalue of sigma. Yes, so for example, the order of sigma is 2, then lambda sigma is -1, and yes, this measurement is only for j equals 0 and j equals 1. So when the order of sigma is 2, this condition is nothing but the GKM condition. Right? Yes, this condition is true, but this condition seems strange for me, because if we have some topological space whose cohomology ring is coinvariant ring of some pseudo-reflection group, and if such space has some structure like Fourier decomposition, then we can compute the cohomology ring, the equivalent cohomology ring of such space by Meyer-Beatrice sequence. But, however, this condition requires us to know all information of higher dimensional cells when we attach the first two-dimensional cell, right? So this condition is if sigma is not 2, so when we attach the first two-dimensional cell, and calculate the equivalent cohomology ring, but this condition requires us to know all information of higher dimensional cells. Right? Let's see. So I rewrote this condition choose a linear order on W sigma W sigma square W dot sigma W, and we'll write it for every pseudo-reflection sigma and actually we need it is too much let's see, I want to say is my term is star is map, this F is map in this way CV which satisfies for every sigma, reflection sigma, and every elements of W first. Oops. F of sigma I1W and sigma I2W 1. This determinant is contained in sigma, and contained in W sigma I W sigma W 1 and sigma I1 sigma the I2's power I0's power sigma I1 one's power sigma I sigma's power, and this determinant is contained in from sigma of alpha sigma the order is power so of course we can verify these conditions by yes. Wow, that to say, but look at this condition. This condition is nothing but the original GKM condition, right? F minus product of these. And if we attach the first two-dimensional cell, this condition appears, and the next cell, we attach the next cell, this condition appears, and so on. So yes, this description is suitable for the desired some structure like Boolean decomposition. So, but we don't know any natural partial order like Boolean order on pseudo-reflection groups. So, if we find such natural partial order, then I think that I believe that we can construct some topological space which is an analog of a flag manifold in the case of pseudo-reflection group. Thank you.